In this presentation on relations and functions, we are going to discuss certain problems related to equivalence relation and equivalence class. Now the first question we have is, let X be a non-empty set and S be the collection of all subsets of X, and R is the relation on S, and it is defined in this form. We are saying that A and B are related if A is a proper subset of B. So a proper subset means that it is a subset of that set, and the set A is not equal to the set B. So we can look at this situation in this form. We are saying A is a subset of B, but A is not equal to B. Now we have to prove that this relation R is transitive, but it is neither reflexive nor symmetric. So first of all, we are going to prove that it is transitive. So we are saying let A, B, C, they belongs to S, that is this collection of all subsets of this set X. And we are saying A and B, they are related by this relation, that is A is a subset of B, and we are saying B is a subset of C. So we can look at this situation in this way. We are saying A is a subset of B and B is a subset of C. So it is clear over here from this figure that A will be a subset of C. So what we obtain from this, we are saying this implies us that A and C, they are related by the relation R. So we have proved that if A and B are related, B and C are related, then A and C are related. So it means that this relation, it is transitive. Next, we have to prove that it is neither reflexive nor symmetric. So to prove it is not reflexive, we are going to give an example. So we are saying let A be any set, and we know that A is not a proper subset of A because A is equal to A, and the condition we have over here is that it should be a proper subset. We are saying it should be a proper subset. So what we obtain from this is that A is not related to itself. Next we have is non-symmetry. So when we are talking about non-symmetry, we are considering the element A comma B belongs to R. A comma B belongs to R means we are saying that A is a subset of B. And we know that if A is a subset of B, then B cannot be a subset of A unless A and B, they are equal to each other. The condition we have is A is a proper subset of B. So we are saying that B cannot be a proper subset of A. So this implies us that B is not related to A by this relation R. So what we have obtained, that for A comma B belongs to R, B comma A does not belong to R. So we are saying that this relation is not a symmetric relation. Now the next question we have is, let n be the set of all natural numbers. So n is the set containing elements 1, 2, 3, 4 and so on. And R is a relation on n cross n. So what will be the elements of n cross n? N cross n will have elements in this form. We are saying it will have elements 1, 1, 1, 2, 1, 3. So these are in the form of ordered pairs. Now the relation R is defined on this. So when we are talking about the relation, we are saying it is defined over here. We are saying A comma B is related to C comma D. This implies us that AD is equal to BC. So if we are saying that 4 comma 2, it is an element of n cross n. It is related to 9 comma 18. These two elements, they are related to each other because we have A into D, that is 4 into 9, that is equal to B into C, that is 2 into 18. So this relation, it is defined on n cross n and it is not defined on n. So this thing you should keep in mind while solving this problem. Now we have to prove that R is an equivalence relation. So to prove that it is an equivalence relation, first we are going to check the reflexivity. So we are considering any element of n cross n. We are not considering the element of n. We are considering the element of n cross n, the ordered pair n cross n. And we are saying AB belongs to n. So we are checking this condition whether AB is related to AB. And this thing will hold because we have, from the definition of this relation, we are saying AB is related to AB because if we take the product A into B, that will be equal to B into A. So we are saying that this relation, it is a reflexive relation. Now second, we have to prove that this relation, it is symmetric. So we are considering the element A comma B of n cross n. And we are saying suppose it is related to another element of n cross n, that is C comma D. Now AB is related to CD. We are considering this thing. This will imply us that AD is equal to BC. So we can write this statement in this form. We are saying this implies us BC is equal to AD. And this thing, B and C, they are the natural numbers. So what we obtain is that the product is commutative. So we obtain that CB is equal to DA. And by the definition of this relation, when we are saying CB is equal to DA, it means by the definition of this relation, we have CD is related to AB. So what we have obtained, that whenever the element A comma B we are talking about, it is related to the element C comma D, then we have this element C comma D of n cross n. It is related to the element A comma B of n cross n. So this relation, we are saying it is symmetric relation. Next we have to prove is the transitivity. So we are considering three elements. One element we are saying it is A comma B, and we are saying suppose this element is related to the element C comma D. These are the elements of n cross n. Next we are considering that C comma D is related to some element of n cross n, it is E comma F. So from this first case, we are talking about A comma B is related to C comma D. We obtain that AD is equal to BC. And from this second case, we obtain that CF is equal to DE. Now, if we take the product of both these equations, what we obtain is, we are saying this implies that AD equal to BC. We are multiplying this second equation over here. We obtain it as CF into DE. So from this relation, we can write it in the form that AF into CD, that is equal to BE into CD. So what this whole thing implies us that AF is equal to BE. And if AF is equal to BE, then again using this condition of the relation, we are saying if AF is equal to BE, then this implies us that AB is related to EF. So we have proved that if AB is related to CD and CD is related to EF, then AB is related to EF. So we have obtained that this relation is transitive, and we know that a relation which is reflexive, symmetric and transitive, that is an equivalence relation. Now next question we have is, if R1 and R2, these are two equivalence relations on a set A, we have to prove that intersection R1 intersection R2, it is also an equivalence relation on A. So first of all, we are going to prove that R1 intersection R2 is a relation. So we are saying that R1, it is a subset of A cross A. If it is R1 is a relation on A, it means R1 is a subset of A cross A. R2 is a relation, so it means R2 is a subset of A cross A. So this implies us that R1 intersection R2 is a subset of A cross A. So what we obtain from this is that R1 intersection R2 is a relation on A. So this is the first thing we have proved, that R1 intersection R2 will be a relation. Now we have to prove that this relation R1 intersection R2, it is an equivalence relation. So first of all, we are talking about the reflexivity. So we are saying it is given that R1 is reflexive and R2 is reflexive. So if R1 is reflexive, it means that A comma A belongs to R1. That is, the element A is related to itself by relation R1. And if R2 is reflexive, it means that A comma A belongs to R2. And these two things, they hold for all A belongs to the set A. So this is by the definition of reflexivity of the relation R1 and R2. Now look at these two conditions. We are saying A comma A belongs to R1, A comma A belongs to R2. So combining both these conditions, we obtain that A comma A belongs to R1 intersection R2 for all A belonging to the set A. So this thing proves that, this implies us that R1 intersection R2 is reflexive. We have proved that for every element A is related to A by this new relation R1 intersection R2. So it is reflexive. Second thing we have to prove is that it is symmetric. So to prove it is symmetric, we are saying let A, B, they are related to each other by this relation R1 intersection R2. Now we are saying that if A and B, they are related by this relation, it means that A and B, this set A and B we are talking about, it belongs to R1. This ordered pair we are talking about, it belongs to R1. And this ordered pair AB, it also belongs to R2 because it is present in the intersection of R1 and R2. It means it is present in R1, it is present in R2. So this implies us that B comma A belongs to R1 because we have R1 is equivalence relation. It means R1 will be symmetric. So if R1 is symmetric, we are saying AB belongs to R1, then BA will belong to R1. Similarly, R2 is symmetric and AB belongs to R2. So we have B comma A belongs to R2. So what we have obtained over here is that this B comma is an element of R1, B comma is an element of R2. It means that B comma A is an element of R1 intersection R2. So what we have obtained, that if A, B, it belongs to intersection of R1, R2, then we have B, A, it will also belong to the intersection of R1 and R2. So we obtain that this relation, it is a symmetric relation. Now next thing we have to prove it is transitivity. So we are saying that it is given that R1 and R2, they are equivalence relation. It means they are also transitive. So to prove transitivity, we are considering two elements. We are saying A comma B belongs to R1 intersection R2. We are considering another element. We are saying B comma C, it belongs to R1 intersection R2. Now to prove that this is transitive, we have to prove that A comma C belongs to R1 intersection R2. Now from this first condition, we get that A comma B belongs to R1 and A comma B belongs to R2 because we are saying this ordered pair AB, it belongs to R1 intersection R2. It means it belongs to R1. It also belongs to R2. Similarly, we have B comma C, it belongs to R1 and B comma C, it belongs to R2. Now we have this relation R1 and R2. Both these relations, they are equivalence relations. We have the conditions that A comma B belongs to R1. Look at this value over here. We are saying A comma B belongs to R1, B comma C belongs to R1. So we combine these two results. We are saying A comma B belongs to R1, B comma C belongs to R1. Then we have A comma B belongs to R2, B comma C belongs to R2. So we are writing and A comma B belongs to R2, B comma C belongs to R2. Now R1 is an equivalence relation, is transitive. It means what we obtain from this is that A comma C belongs to R1. R2 is transitive. So this implies us that A comma C belongs to R2. So what we have obtained over here is that A comma C belongs to R1, A comma C belongs to R2. It means that A comma C, it will belong to intersection of R1 and R2. So this proves that R1 intersection R2 is transitive. So we have obtained, the first thing we have proved over here is that R1 intersection R2 is a relation. We have proved that it is reflexive, it is symmetric, it is transitive. So we are saying that R1 intersection R2 is an equivalence relation on A. Next is give an example to show that the union of two equivalence relations on a set A need not be an equivalence relation on A. So we have to give an example to prove that it is not an equivalence relation. The union is not an equivalence relation. So we are considering the set A. It consists of elements 1, 2, 3. We are defining two relations on it. We are saying the relation R1 is there. It contains 1, 1, 2, 2, 3, 3, 1, 2, 2, 1. So clearly this relation is an equivalence relation. It is symmetric, transitive, and reflexive. We define another relation R2. It is 1, 1, 2, 2, 3, 3. These elements are there. And then we have the element 1, 3, and 3, 1. So both these relations, we can verify that both these relations, they are R1 and R2, they are equivalence relations. Now if we talk about the union of this relation, we are talking about R1 union R2. We have the elements, it is 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 1, 3, and 3, 1. This is the union of these two relations. Now if we consider the element 3, 1 from this relation, we have this element 3, 1, and this belongs to R1 union R2. We consider another element, say 1, 2 from this relation. We are talking about this element 1, 2, and we are saying it belongs to R1 union R2. But what we can see from this, that there is no element 3, 2 in R1 union R2. It means that this relation R1 union R2 is not a transitive relation. So we have proved that this example proves that the union of two relations, it need not be the union of two equivalence relations need not be an equivalence relation. Now the next question we have is, let A be the set of all lines in xy plane, and R is a relation on A. It is defined like two lines L1 and L2, they are related by this relation if L1 is parallel to L2. We have to prove that R is an equivalence relation in A. So to prove the reflexivity, we can use the fact that every line is parallel to itself. So we are saying that for every line in A, every line is parallel to itself. It means that L comma L belongs to R for all L belongs to A. For symmetry, we are using the fact that if a line is parallel to another line, we are saying L1 is parallel to L2, then this second line L2 is also parallel to L1. So this implies us that if L1 and L2 are related, then L2 and L1 are also related. So this thing just means that if the first line is parallel to second, then the second line is also parallel to the first line. Next we have is transitivity. So for transitivity, we are considering three lines. and we are saying that line 1 is parallel to line 2 and line 2 is parallel to line 3. We are talking about this condition that line 1 is parallel to line 2 and line 2 is parallel to line 3. Then clearly we have that line 1 will be parallel to line 3. It means that L1 will be related to L3 by this relation. So we have proved that this relation, it is reflexive, symmetric and transitive. Now next thing we have to find in this question is find the set of all lines related to the line y is equal to 3x plus 5. So when we are talking about this line y is equal to 3x plus 5, the slope of this line we have it is equal to 3. So we are saying we are interested in finding all the lines which are related to this line by this relation. It means we are interested to find the lines which are parallel to this given line. So we are saying the family of all lines parallel to the line y is equal to 3x plus 5. They are given by the relation y is equal to 3x plus k, because the slope it is 3. We are talking about the given equation is y is equal to 3x plus 5. Slope we have it is 3. To find the lines parallel to this line, we are writing y is equal to 3x plus k. So these are the family of lines which have slope 3, where we are saying this k is a real number. So these are the required lines which are related to this line by this relation. That is, we are interested in calculating all the lines parallel to the given line. Now the next question we have is, let A be the set consisting of integers such that 0 is less than equal to x is less than equal to 12. It means A has the elements 0, 1, 2, 3, 4, so on up to 12. We are saying these are the elements of A. Now we have to show that the relation are defined like that two integers they are related if mod of A minus B is a multiple of 4. We have to prove that this relation is reflexive, symmetric and transitive. So to prove that it is reflexive, we are considering an element or integer A from the set A, and clearly we have A minus A is equal to 0. So this implies us that this number 0 it is multiple of 4. So this implies us that A is related to itself for all A belongs to A. Next, to prove the symmetry, we are saying let A and B, these are two elements which are related to each other. So if A is related to B, then clearly we have A minus B is a multiple of 4. It is by the definition of this relation. So if A minus B is a multiple of 4, it means B minus A is a multiple of 4. Then by the definition of this relation, we have B and A, these two elements, they are also related by this relation R. So we have proved that if A is related to B, then B is related to A. It means this relation, it is symmetric. Next, for transitivity, we are saying let A and B, they are related, and B and C, they are related. So if A and B are related, it means A minus B is a multiple of 4. And if B and C are related, it means B minus C is a multiple of 4. Now if A minus B is a multiple of 4, it means there exists some number k1 such that A minus B is equal to 4 times k1. It is a multiple of 4. And B minus C, it is a multiple of 4. It means B minus C is equal to 4 times some number k2. Now we have to check whether A and C are related or not. So we are calculating the value of mod of A minus C. Now if we substitute, add and subtract B over here, we are talking about this value. What we have done, we have added and subtracted B to these values. Then we obtain that A minus B is k1 and mod of B minus C is 4 times k2. So we are saying that this value we obtain, it is equal to 4 times k1 minus 4 times k2. Now if we take 4 common from this term, if we write 4 common from this term, we are saying this is equal to 4 times k1 minus k2. So what we have obtained that A minus C, we're talking about this term A minus C mod, it is equal to 4 times K1 minus K2. It means A minus C mod is a multiple of 4. So this implies us that A is related to C. Now next we have to prove is that we have to find the set of elements related to 1. So set of elements related to 1 means we are interested in calculating this value, that we are interested in those values, those elements of A for which x is related to 1. So x is related to 1 means we are trying to find those x which are related to 1. It means we are saying we are trying to find those x for which x mod of x minus A or x minus 1 is a multiple of 4. Now x minus 1 is a multiple of 4 means if we look at the elements of the set A, we are calculating the value of mod of 1 minus 1. So it is a multiple of 4. If we take the value of x is equal to 2, we have mod of 2 minus 1, that is 1, and it is not a multiple of 4. Similarly, for this third element 3, mod of 3 minus 1 is equal to 2, it is not a multiple of 4. 4 minus 1 is 3, it is not a multiple of 4. 5 minus 1 is 4 and it is a multiple of 4. Next 6 minus 1 is 5, it is not a multiple of 4. So continuing in this way, we can obtain that what numbers are there for which x minus 1 is a multiple of 4. We have obtained the numbers in the form they are 1, 5 and 9. So these are the numbers which are related to the integer 1 corresponding to this relation R. So this is the answer, that the elements 1, 5, 9, these are the 3 elements that are related to the number 1. Now the next definition we have it is equivalence class. So for equivalence class, the first condition we have is that we have a relation R which is an equivalence relation on a set A, and we have an element A belongs to A. We have an element of this set A. Then we are talking about the equivalence class determined by this element. So equivalence class determined by this element, it is basically the set of all those elements of A which are related to A by this relation R. And this equivalence class, it is denoted by this symbol. So we are saying equivalence class of any element A of A, it is equal to those elements of this set which are related to the given element A by this relation R. So this definition will be more clear to you with our next example. Suppose we are saying that we have a relation R that is equal to A and B are related if A minus B is divisible by 3. And this is a relation on the set of integers. So first of all, we are proving that R is an equivalence relation on Z. So to prove that it is an equivalence relation, first we are considering the reflexivity. We are saying if we consider some element A belongs to Z, that is A is an integer, then A minus A is 0, which is divisible by 3. So we are saying that every element over here, it is related to itself by this relation. So it is a reflexive relation. Next, to prove symmetry, we are saying if A and B, these are two integers, such that A and B are related. A and B are related means A minus B is divisible by 3. So we know that if A minus B is divisible by 3, then minus of A minus B is also divisible by 3. It means B minus A is divisible by 3. So if B minus A is divisible by 3, then by the definition of this relation, we are saying A and B are related if A minus B is divisible by 3. So if B minus A is divisible by 3, we obtain that B is related to A. Next we have is the transitivity. So we are saying let A and B and C, these are the 3 elements we have, such that A is related to B and B is related to C. So A is related to B implies that A minus B is divisible by 3. B is related to C implies B minus C is divisible by 3. So if A minus B is divisible by 3, we are talking about the value. We can write that we have A minus B is divisible by 3. It means that we have some number k such that k1 such that A minus B is equal to 3 times k1. If B minus C is divisible by 3, it means we are saying B minus C is equal to some number k2 is there such that 3 times k2. So what we obtain from this is that the number mod of A minus B plus B minus C, if we talk about this value, we add both these values, that is also divisible by 3. So this proves that A minus C is divisible by 3. So we have proved A minus C is divisible by 3. This implies us, so this thing implies us that A is related to C. So we have proved that this relation, it is transitive. So combining all these three results, we are saying it is reflexive, symmetric and transitive. We obtain that this relation R, it is an equivalence relation on Z. Now next we have to find, the next part is find the partitioning of Z into mutually disjoint equivalence classes. Now we will see that what this term mutually disjoint equivalence classes. So we are going to answer this question, that we have to find the partitioning of Z into mutually disjoint equivalent classes. First of all, we are taking this integer 0, and we are calculating the equivalence class corresponding to this number 0. So equivalence class corresponding to 0 means we are interested in those integers Z which are related to 0. It means by the definition of this relation we are interested in those integers for which x minus 0 is divisible by 3. So we are saying the integers for which x minus 0 is divisible by 3, they are 0, 3, 6, 9, so on, and minus 3, minus 6, and so on. So we are saying these are the elements which are related to 0. So what we obtain is equivalence class of 0, it is this set. So all these elements, these are related to 0 by this relation. Next we are talking about the next element, it is 1. So equivalence class of 1 is those integers which are related to 1. So we are saying this is equal to those integers for which x minus 1 is divisible by 3. So the integers for which x minus 1 is divisible by 3, they are 1, 4, 7, 10, so on, and minus 2, minus 5, and so on. So what we obtain is that the equivalence class corresponding to 1, it is this class. Next, suppose we are calculating the equivalence class corresponding to 2. Then we are saying all those integers for which x is related to 2. It means we are talking about that x minus 2 is divisible by 3. So if x minus 2 is divisible by 3, the elements we have, these are the elements that we have. So we obtain that equivalence class corresponding to 2, it consists of these elements. Now suppose we try to find the equivalence class corresponding to 3. So equivalence class corresponding to 3 means we are talking about 3. It means we are interested in those integers Z for which x is related to 3. It means we are talking about those integers Z for which x minus 3 is divisible by 3. So what are the elements over here? We list these elements. The collection we obtain, it is 0, 3, 6, 9, so on. Or the elements we have, it is minus 3, minus 6, and so on. So look at these values over here. Look at these values over here. We are saying the equivalence class of 0, when we are talking about, that is equal to the equivalence class of 3. That will be equal to equivalence class of 6. That will be equal to equivalence class of 9. So what we are saying over here is that these are the equivalence classes that we have. we are saying equivalence class of 0, equivalence class of 1 and equivalence class of 2. These are mutually disjoint. Mutually disjoint means that intersection of equivalence class of 1 and 0, it is 5. The intersection of equivalence class of 1 and 2 is 5. The intersection of equivalence class of 0 and 2 is 5. And moreover, we have the set of integers. We can write it is equal to equivalence class of 0 union equivalence class of 1 union equivalence class of 2. So this thing, we can look at this figure over here. We are saying that we have this complete figure. This is representing the set of integers. We are saying we have equivalence class of 0. Equivalence class of 0, when we are saying it has the elements 0, 3, 6, 9, then -3, -6, so on. Then we have the equivalence class of 1. We have the elements 1, 4, 7, 10, so on, and we have the elements -2, -5, so on. Then we have equivalence class of 2. We are saying the elements we have it is 2, 5, 8, 11, so on, and negative numbers we have it is -1, -4, and so on. So we are saying what we have done, we have partitioned this set of integers in 3 mutually disjoint equivalence classes. So we have 2 results over here. First is that 2 equivalence classes are either disjoint or they are identical. This thing we have seen, that if we are talking about the 2 disjoint classes, we are talking about the equivalence class 0 and equivalence class 1. Either they will be, their intersection is 5. If we are talking about the equivalence class of 0 and equivalence class of 3, these two, they are equal. So we are saying if we consider 2 equivalence classes, either they are disjoint or they are identical. And second thing we have observed over here is that an equivalence class, that an equivalence relation R on a set A, it partitions the set into mutually disjoint equivalent classes. So this thing we have seen, that how it is going, it has partitioned the set of integers into mutually disjoint equivalence classes. Now next we have is, let A be the set. It consists of the elements 1, 2, 3, 4, so on up to 9, and R be the relation defined on A cross A. It is important to note over here. Now the relation, it is defined on A cross A. It is defined in this way. We are saying element AB is related to element CD if and only if A plus D is equal to B plus C for all AB and CD belonging to A cross A. Now we have to prove that R is an equivalence relation. So to prove it is equivalence relation, first of all we are considering reflexivity. We consider any element AB belongs to A cross A, this Cartesian product. So we are saying that A and B, they belong to A. So what we have is, this implies us that A plus B, that is equal to B plus A. So this implies us that A comma B is related to A comma B. That is, every element is related to itself. This condition we are getting, we are writing A plus B is equal to A plus B. We are writing it from this condition of the relation. So we have proved that this relation, it is reflexive. Next we have to prove that this relation, it is symmetric. So we are considering that there are 2 elements AB and CD such that AB is related to CD. So by using the definition of this relation, we have A plus D, that is equal to B plus C. Now by commutative law, we have C plus B is equal to D plus A. Now again, using the condition of this relation, we obtain that this implies us that C comma D is related to A comma B. So we have proved that whenever A, B is related to C, D, then C comma D, that will be related to A comma B. Now last thing we have to prove it is transitivity. So for transitivity, we are saying we have considered 3 elements. A, B is related to CD and CD is related to EF. Then using the condition of this relation, we are saying if AB is related to CD, it means A plus D is equal to B plus C. And if CD is related to EF, we have C plus F is equal to D plus E. Now if we add both these equations, we have A plus D plus C plus F. If we add these equations, we obtain A plus D plus C plus F, that is equal to B plus C plus D plus E. So from if we simplify these terms, we cancel the common terms on the both sides. We obtain this implies as A plus F is equal to B plus E. Now again look at the condition of this relation. If we have A plus F is equal to B plus E, so this means that A comma B, it is related to E comma F. So we are saying that if AB is related to CD and CD is related to EF, in that case AB is related to EF. So we have proved that this relation, it is transitive relation. So as this relation, it is reflexive, symmetric and transitive, so it is an equivalence relation. Now next part we have is we have to find the equivalence class determined by the element 2 comma 5. So when we are talking about this equivalence class of 2 comma 5, it means we are saying we are talking about equivalence class of 2 comma 5. We are interested in those elements A, B for which are related to this element 2 comma 5. Now by the definition of this relation, we have if these elements, these are related to 2 comma 5, so what we obtain from the definition is we are interested in those elements A, B for which 2 plus B is equal to 5 plus A. Solving this, we obtain we are interested in those A, B for which B minus A is equal to 3. Now corresponding to these elements, if we calculate the values, we can find that 4 minus 1 is 3. We have 5 minus 2 is 3. We have 6 minus 3 is 3. We have 7 minus 4 is 3. We have 8 minus 5 is 3. And 9 minus 6 is 3. So what are the elements A, B we have? We are saying that for 1 comma 4, 2 comma 5, 3 comma 6, 4 comma 7, 5 comma 8 and 6 comma 9. We have these are the elements which are related to the element 2 comma 5. So the equivalence class of this element 2 comma 5, it consists of these elements.